Okay, shall we start now? Right. Today we are going to see the stack and subroutine in 8085. Right. Here the stack is actually last in first out structure. Last in first out structure, right? So we are having now the structure is last in first out. Last in first out structure, right? So we are having now the structure is last in first out structure. The stack is actually growing in the upwards, right? So here we are having now it will grow in the backward is actually here we consider now if you are having that address is 9f, then we are adding the data, or we can call it as push and pop, right? If you are having a stack, then we are having that operation is push and pop operation. So we are pushing the data, then the first data we are going to push in 9ff, right? So that is we are having now in that particular case we are going to fill that one, right? The next address is 9ff. So automatically it will decrement now the next address, then we are storing now, right? Like it will store one by one in the direction, right? So it is decrementing that each and every push operations. Now the reverse is pop operation. We are popping the data from outside, right? So we can pop the data from out, right? So that we are want to take the data is pop out, right? So the pop out is here we are popping out, right? So push is we are going to push that one, right? So here we are having now push data, push and pop, right? So this is the operation actually we are doing. So that is we are having now last in first out structure. Okay. If you are having doubt, you can stop me. You can ask question, right? Sure. Now here we are having now that I told you that one 9ff. Then here we are having now the 4ff is the bottommost address, right? So the last one is we are having now 4ff, right? Then we are decreasing that one as ff then ff e d, then ff c, ff b, right? Then f of a, then we are having now one to join. Okay, one minute. Om Prakash. Okay, right. So here we are having now f of a. Then we are having now the next one is here we are having now f9. So and so on. Then it is decrementing while pushing the data, right? While popping the data. So this is actually stack pointer address. So the stack pointer is a pointer where the top of the stack is the address where we can push the data. Then whenever we are popping out, then it will increase that one, and while pushing that one, then it is decrementing and it will grow in the backward direction. Backward direction means the address is going to be reduced. So that is we are having now, right? So here we are having now that there is no limitations. So here we are starting from f up, then it will grow upwards, then it may reach some other locations, right? So here we are having voluminous data is available that we can push many number of data. This is stack pointer, right? So how do you load the stack pointers? We are having that we know that one LXI, right? Load register pair immediate. LXI is load X is register pair. Load register pair immediate. Then the register pair that is stack pointer. The stack pointer is 16-bit, right? So 16-bit, and then we are placing the 16-bit is f of f, right? So this is a stack pointer. So in that architecture, you know that one where it is stack pointer. So now here we are having now for placing the data we are using the pushing, right? So pushing it, right, to save on the disk, right? So on the stack you want to save the data on the stack, then you use that instruction called push. Push is the instruction we can use, right? Then retrieving from the stack, we are retrieving from the stack, we can use pop operation. So this is the operation, right? So push and pop, right? Push is the saving, then pop is retrieving. Okay, now here push and pop operation is going to be used, then push and pop operation is going to use for register pair. So always it will push 16-bit data, right? So here for simple example, push a, right? Then we are having now, okay, we are push A, then this is actually we are having program status word, PSW, program status word. The program status word is A register as along with the flag register content. So flag register content also is going to be same, combined together, right? So we are having now, right? So now you'll see that one, the instruction is push P. So that push B, then we are having PE pair is going to be pushed. So that the instruction is only push P, but it will take a pair register. So P register content is in the top, then we are having now higher and then lower is going to be loaded into the stack. Higher and lower is going to be loaded into the stack, right? So the stack pointer is there. So stack pointer is currently here, then we are adding the data, then it will decrement and place the data, decrement, place the data, right? Now the pointer is showing that one, right? So SP is, now we are having FFFD. Whenever we are pushing, then it will decrement and push the data. Then pop operation is in the reverse, right? So we are popping in the we are in the PE pair and then popping into TE pair, right? So we are exchanging the data, we are moving the data from PC to DE, moving the data PC to TE, moving the data PC to TE. Okay, moving the data PC to TE we are having now, right? So that one is here, what you are pushing through the PC pair is pushing now, then the same data we are popping to DE pair, right? So just we are having the whatever the PC pair we are copying now using stack, right? So we are popping now, right? While popping the lower first and then higher next. So we are decrementing, the pointer is decrement, increment, and to reach the empty stack, right? Now in that operation on the stack is, we know that one, use the increment or decrement that corresponding data, right? Now I already told you that one. So if you are we are storing that content of BC pair, PC pair and the D pair. So we are having now the 4-byte address, right? So B, C, D, E are stored, right? Then the stack pointer is showing that location. So we are having now, right? Next we are once again, then after doing something, then we are popping D. Pop D is the whatever the DE pair content, once again then return back to DE pair. So that content is popped and it is placed in E, then pop, it is placed into D. So we can push that in the reverse direction, we have to pop because of last in first out. So we have to consider now last in first out manner we are storing. So here we have to, whatever in that order we are pushing, now in the reverse order we have to pop it, right? So pop in the reverse order we have to pop. Okay, that is we are having now the content instruction. Next we are having now the program status, what I told you that one, pop push A. So that is called accumulator along with that flag register, right? So the accumulator and flag register content combined together is 16-bit, right? Accumulator one 8-bit, then followed by, then we are flag register is another 8-bit. So the total 16-bit is there. That is called program status word, right? So we are having the instruction is called push PSW, right? Not stack. Push PSW. We are having the instruction is push PSW, program status word, right? So that is A register content first and then flag register content next. So we are storing now, right? So the higher is first and then we are having now A register content and then flag register content is going to be stored in this top of the stack, right? Then pop PSW, so we are popping that reverse order, we are popping now, right? So that is lower is going to have that flag, and then next one is we are going to have now the A register. So whatever that we are storing, we are retrieving that one using push and pop. Now here all of you know that one, the flag register content, right? So flag register content is we are having the 0th bit is carry and 1 bit is not used. Second bit is we are having parity, third bit is not using, and fourth bit is auxiliary carry, fifth bit is not using, and sixth bit is 0, and seventh bit is yes 0 sign, right? So sign 0, auxiliary carry, parity, carry. So every time if you are telling now, then we will have that familiar with that sign 0, auxiliary carry, parity, normal carry, right? Now you see that one, we are having that LXI SP FF, right? So the stack pointer is defined as the base address. This is FF1 location, memory location, right? Then we are having the push PSW. This instruction is doing now. Then we are having the 8 accumulator, and then we are having flag register content. We are loading, right? Then you are having now this is FFE. Then this is come to FFD. This is the location, right? Next we are having now push pop H. We are popping H, right? Now what it will do now in the HL, right? So here in that L register contain in flag register content, then we are having now pop that H. So that one as A is copied into H, and flag register content is copied into L through the stack. So we are retrieving the stack, right? Pushing the data and popping the data. Next move L comma L to E, right? So the L content, the flag register content is going move to then accumulator. Move to accumulator. So accumulator means this accumulator, right? So that accumulator is changing now, right? Move A comma L. A comma L is, so L register content, popping that one, the L register content, flag register content come to the accumulator, right? So that is flag register content, we are getting the data to that one, right? Now then we want to change that flag register. So here we are changing the flag register is here we are having to immediate operation, right? So that is we are having now 1011, right? Then we are having now all are 1. We are doing the AND operation. So it will show that one what is the carry flag currently, then what is the parity flag, then we are having now what is the auxiliary carry, then here the 0 flag is not showing now, then sign flag is what is going on. So that is we are having now, it will have that one and immediate with, right? So and immediate means, so we are having this is one, this is if this is one, then this is one, we are getting now the result is the flag register content, the accumulator content is and, right? So and that PM, so PM nothing is that, this is actually binary value. So B, this is B, right? So 11, this is 8, this is 2 1, 8 plus 10 11, right? So this is F, 8 4 2 1, right? So 8 4 12 12 to 12 to 14 14 1 15, right? So that is, so if you are having intermediate with PF, then it will have that one. If we are having carry 1 and this one, then we are having that as 1, right? So wherever we are having each bit is checking now for both are 1, then we are having the corresponding 1, right? So that is we are having now the result. Now the result is going to place once again that L register. So the L register is now the flag is modified, and we are placing that to L. So we are taking from L and we are modifying and placing the data into L register. Then the HL pair is going to be pushed, and then we have to get back to program status where now the flag register content is modified according to the intermediate operation. So we are doing now the changing the flag register content using stack, right? Modify that is modify the flag register content, right? Using push and pop operation. Modify the flag register content using push and pop operation, right? So that 2 more question they may ask, right? They may ask question as modify the content using the push and pop. Then you have to write that this statement. Anybody is having doubts whether it is going clearly or if you are having some problems? So Rakesh, any one of you, then unmute yourself, you talk with me, right? ராகேஷ் ஹாஸ்டலுக்கு சாப்பிட போயிட்டானா?
சார் இங்கே தான் சார் இருக்கு.
ஆ இல்லை கண்டினியூஸாக வருதா?
வருது சார்.
ஓகே. அண்டர்ஸ்டாண்ட் பண்ணுங்க. நான் வேஸ்ட்டாக பேசிகிட்டு இருக்க மாதிரி இருக்குது. எல்லாம் எவ்ரி ஒன் ஷுட் அண்டர்ஸ்டாண்ட் நவ், ரைட்? சரி, go to next. Right. Here actually the stack is used by subroutine, right? So here we are having now the subroutine. I told you that one subroutine is nothing but a function, right? Subroutine is a group of instruction. So this is one function. Subroutine is a group of instruction that is used repeatedly in different location of the program, right? So function call, as like a function call, it is called subroutine in the case of assembly language program, right? Then we want to repeatedly is doing some operation, then the operation is placed as a subroutine. Then in your main program, wherever you want to call the subroutine, we are calling now in many places, right? So that is, you call it as subroutine. So in C language you consider it a function. So the function we can call repeatedly in the program. Similarly, we are creating one subroutine. If the code is repeated, then we are creating a subroutine wherever you want, then we can call the subroutine. So that is the subroutine, right? In we are having now, we can have the subroutine and we can call it anywhere else, right? Here we are having now the for calling the subroutine, we are having that instruction called call, right? Call is a instruction. Then using that instruction we can call the subroutine. So call followed by one address. In that address we are having now subroutine address. So in that address we are having a list of instruction for the particular subroutine execution, right? So that is this address. This address is there in the call function followed by that address. Now this address is going to be loaded into program counter, then it will continue to execute. Then we are having in the at the other end we are having return. Then while return, then it will come to the next statement of your main program. So we are having the call and return is used for subroutine call, and we are return from subroutine. So that instruction we are using now, call instruction, right? So call with 4000, right? Now I am having 8500 is the location where we are having one subroutine. Now your program start with that 8000. In that 8000 you are starting your program, right? Then one statement is here we are having call 8500. That is here 8500. Now we are calling the function, right? So we are calling that function. What it will do now, while calling that function, then our control will go to here and then it is executing, right? Then here at the end we are having return function. It will return to the next address, next address of function call. So this is the next address we are returning, right? So that is we are going to have now, right? Now you see this one here we are having that 4000. The 4000 is loaded into PC, right? So that we are having now that actually before that what actually it will do now, this particular return address 2003, right? So the after calling, then we are going to return this location. So that value 2003 is going to be 2003 is going to be, right? So 2003 currently now in program counter. The program counter content is preserved in the stack. So in the stack we are pushing the PC value now, right? So what is the current location? The next location where we are going to return, that location is going to be saved in the stack pointer using stack pointer. So we are saving the data in the stack pointer. Kumar, you are raising your hands. What do you need? Nothing? Kumar? Okay. Right. So PC value, PC data is going to be stored, and then we are having now that your control will go to the PC. Once again the PC is loaded with 4000, right? Then that is available in the WSET register, and it is going to be placed in the PC pair. So the PC pair is going to start now that location. Okay. Sure. Oh, if this is a call instruction, then the call instruction is at the end. We are having now the return address. Then the return is here. We are whatever the store in the stack of the program counter value previously called, then we are having now that return to 2003. So that 2003 is in PC. Now automatically it will return. So the in that 40515 we are having return address. The return address will do that operation of popping that stack on PC, popping the stack on PC. Then the program counter content is 2003. So our main program is after call function we are returning to the 2003 is a location. Right. Okay. Now here what we have to consider now, right? So here we are having now, then you must set the stack pointer correctly before using call instruction. So we check that one whether the stack pointer is already set. Then we are calling, right? Or otherwise, what it will happen here? Stack may give some other location that may not be a memory. Then we are call instruction. Then it won't save that one. Then while returning, then we can't get anything, right? So we have to specify the stack pointer before calling the function. Now using the stack pointer, it will call return address. Then properly while return, then it will come back to the original position, right? So suppose the stack pointer is not defined properly, then it will show some other location. Then that increment and decrement using the push and pop is wrong. So you have to be careful with that one, right? So you have to specify the stack pointer before using. We have to consider now, right? So the return instruction is here we are returning using the PC, right? So whatever that in the stack content is going to return back to PC. Then automatically it will return back to the next address of the call function of main program. Okay. So number of push and pop instruction used in subroutine must be same, right? Whatever that pushing, then corresponding one we have to pop, right? So we are using that one container, we are pushing something, then when we want, then we have to pop in that reverse order, and we have to make everything is pop, then it will go for empty. So you have to be careful with the correct address, right? Now the passing data to a subroutine, right? So here we are having the passing parameter in C language as call by reference, call by value, right? That is we are going to see that one, right? So that is call by reference. The data is stored in one of the register. By calling the program, the subroutine uses the value from the register. So we store the content in the register. Then we can use that register for accessing. Right, the register value get modified within the subroutine. Then this modification will be transformed back to the calling program upon returning from subroutine, right? So if you are using that register, so whatever change, then that is retained. Then we can get the register content to the other end, right? So that is we are having now. So that is call by reference, right? So we are having the data with register, then register we have to refer, right? Call by value, right? Then call by value is we are having now that parameter, then the corresponding one we have to call the value, right? So instead of address we are calling by value. Here we are having now the data is stored in one of the register, and then we are having now the push operation, and then we are having now the pop operation. Passing data to a subroutine, right? So here we are having now the calling program store the data in the memory location, and the subroutine retrieve the data from the location and uses it, right? So we can call that many memory locations, right? Then we are having now retrieve the data from the location and use it, right? So we can store and retrieve the data. For that we can use that one location for storing and retrieving the data through that one. Right. So here we are having what is the caution we have to consider in that push and pop. Push and pop should be used in the opposite order, right? I told you that one. In what order we are pushing? In the reverse order we have to popping, then we can get the original data. If the order is changing now, then it will go for that shuffling the data to other registers. So you have to be careful with that. What we are pushing now, the corresponding whether we are popping or not, we have to check. With programmer we have to check. Now we can have a conditional call, right? So call with carry, call with no carry, call with we are having now call with return with call, return with carry flag, then we are having return with no carry flag, etc. Okay, next one is counters and time delay, right? So what it is actually, we want to have that while executing that program, we want to wait for some time for preparing the data. Then what we need to have, we have to make a delay of execution of the particular instruction. So that for that we are having now that delay tactics we have to use by the loop, right? So here we are having initialize, then display and update the content. Is the final count, is the final count? No, then you have to go for loop. By manually we are having now in the loop, right? So we can create a loop, then by the loop we can have the time delay. So we are creating the loop, then what it will do now, the decrement the register continuously. If you are giving that f of, then we are having 255 times is repeated, then each and every time we are elapsing the clocks, then after completion of that one only, then we are having now stop that accessing that memory, right? Right. Now we are having that another program, right? So we are having now, this is the case we have to consider now, move immediate C for f of, right? So move immediate C f of s, we are having now that I told you that one. Here we are having the 7 t state. The last class we discussed about the how many number of t state. If you are having two pair of register, right? So we are having code with 2 byte code. Here we are having now 2 byte code, load C and decrement C, right? Then we are going to jump back to decrement C, right? So we are decrement C now, right? So what is here? Move immediate C. Then we are having decrement C. So we are having now jump no 0, then it will go to the loop. So you until the C is going to be 0, it is repeating now. Okay, sure. Ipo, please, we are having now, you assume that one we are having, I told it, the last class we discussed about that T state for jump no 0, right? Jump no 0, we are having now the opcode, then we are having now the 2 byte address, so totally 3 byte. 3 byte instruction almost we are having now 10 T state, right? So here move immediate is 7 T state. The decrement is 4 T state, right? So 10 plus 4 or 21. So the total T state is here we are having now the 21, right? So here actually we have to consider only 2 instruction in the loop. So the instruction is in the loop. Then here if you are having the C is the number of count, right? So that how do you calculate the number of count for the particular delay time, right? So we are having that this is 2 megahertz. Then one cycle is here we are having now that 0.5 microsecond. Then 5.5 microsecond is multiplied with 70. So we are having now that 3.5 microsecond is used for executing the move immediate instruction. So it is required 3.5 microsecond. So how do you calculate now? So the number of T state required for executing that instruction, each T state is nothing but 1/2 megahertz. 1/2 megahertz. 2 megahertz is 10 power 6, right? So that is we are having now 0.5 into 10 power minus 6, megahertz is 10 power 6. So it come upwards then minus 6. So that is microsecond. Second, then microsecond. 10 power 6 is micro. So that is microsecond. So 0.5 microsecond is required for 1 T state. Then we are having now that 7 T state, then 3 microsecond is required for executing the move immediate instruction. So the first instruction for executing is 3.5 microsecond. Then we are having now the hereafter we are having now this is set of instruction where we are having now that what C value we have to consider for a particular time delay, right? Now you see this one, we are having the time delay for that particular loop, right? So this is a loop. So here the loop is having 14 T state. This loop is having 14 T state, and then we are having each T state is 0.5. So we are having now that one. So this N is actually in the C register content. So C register is going to be loaded with 255. Now it will elapse around 1.8 milliseconds. 1.8 milliseconds, right? Then we are having now loop instruction. We are going to execute now that one, right? So that is we are having now that the last three state we are having remove that one. If you are removing that one 1.5 microsecond we have to remove from our result, then the result is going to have that accurate is 17 7,000 here 1,783.5 microsecond. Right. Now in that way we can calculate the time delay for each and every instruction, right? So that is we are having now the time required for executing this sequence of code is just we are having now this is required LXI can be required 10 T state, then TCX be required 60 T state, right? Then move AC required 4 T state, then here overhead required 4 T state, then jump no 0 is required 10 T state. Right, then this is going to be repeated, so we have to consider now where we are going to repeat it. Now this content is we are taking now the repetition. Okay, so then we are calculating now the repetition through the number. So what is the number? So we are having some number, then we are calculating now 2.5 into 24, then divided by, so the 2.5 0.5 into 24 is 9, so we are having now 109 millisecond. 109 millisecond is required for executing this code. Right? We are having now the data. Right. In the loop, how do you calculate time delay? Right. So we are having now the loop we have to consider. Then the time delay we have to consider. Right? So here we are having now within that one we are having loop one. Right. So this is loop one. Then this is loop two. So within that loop one we are having the loop two. Right. So that is we are having now the delay in loop one. Delay in loop one is here. This is the value. Then delay in loop 2 is here we are having now loop 2 is here we have to consider 0.5 into around 21 T state, then we are having now the TL, and then we are multiplying with 35. So we are having 100 millisecond approximately. So 100 millisecond delay for that particular statement's execution. Check. Next one is flowchart for time delay with two loops, right? So here we are having now the time delay, right? So this is one loop. So this comes under inner loop. So that one is here we are having, suppose we are having the loop is 1000 times, right? This loop is 2000 times, right? So the total is that this particular loop is going to have now 3000. Right. Here we are having now flowchart of counter with the time delay. So flowchart of counter with the time delay. So that is why I can now delay the initialize the register and decrement the delay register. Then we are checking now that it's going to reach the 0. Then yes, then we are getting now the corresponding one as 3. Right. So here we are having now yes. It is not equal to 0. Yes, then it will go for here return. Right. Hexadecimal counter, right? So we are having a counter, then it's going to have a hexadecimal counter, right? So further we are using now P register content and C register content, right? So initially we are having the P register is 0, then we are going to store, then C register is something 1 HC, then we are making now this is we are calling now that delay, that delay is going to call that one, right? So this inner loop, then we are making now outer loop, right? So TCR here next. Right. Right. Here now we are going to illustrate one program as we are calculating a counter from 0 to 9 only. So 0 to 9 only we are going to calculate a counter, right? So here we are having now what we are going to have to that one, right? So the 0 0 is initialized in P register. So P register content is 0 0. Now this content is moved to A register. Now currently A is 0 0. Then we are having now we are sending the output port number, right? So that output, so accumulator content is going outside of that one, right? Then LXI is 16, right? So that is we are having now HL per address. This address is having now then, right? So HL then LXI is 16 bit, right? So that address we are going to have now, right? Then next we are having now decrement HX, right? So HL per currently we are having loaded, and then we go for right? So that we are loading the HL, and then we are having now decrement, then move a mile, right? So the lower is going to have that a, then we are doing now that r operation, ra, then non-zero, then we have to go for low. Okay, right. Then we are having now, then we will go for that increment by b and move that b content to a and compare with the 0 a, whether that we are reaching now 0 or 0 a or not, right? Then if it is 0, then we are going to have now start, else it will display the content. Right here, the in the case of stack and subroutine, these are only content. If you are having doubts, you can ask now. Anybody else? Any one of you? I will tell that name.
No, sir.
No doubt. Chetan. Okay. Anybody else? I'll call by name. Anupama? Okay. Anybody? Paratraj?
No, sir.
No. Okay. Devadarshini? Okay. Now, okay. Do I pen?
No, sir.
No. Shall we continue the next one?
Yes, sir.
Next is we are having now the addressing mode. The next topic is we are having now the addressing mode. Where I stayed. Right. The next topic is we are having now that addressing mode. In that case, we have to consider now. Actually, the addressing mode is used for the memory optimization, performance optimization, reduce the code size of the program, and we can have now flexibility to access the data. So these are all the main advantage of that 8085 in the addressing mode. Right now, we are having that. What are the types of addressing mode? We are going to see that one, right? So the first addressing mode is you have to consider now as so this is the immediate addressing mode. First addressing mode is immediate addressing mode. So the immediate addressing is so move immediate B45 or something, right? So that is we are having now the data is immediate. So the data is immediate, that is called move immediate. So we are moving the data 45 in P register. So P register content is going to have now move the direct data. So that is called move immediate data, right? So that is move immediate, right? Immediate addressing mode. So that is we are having now that immediate addressing mode, immediate addressing, immediate data, right? So that is immediate data. Next one is register addressing mode, right? So that is the register content is going to be move, right? So B comma A. So the P register content is going to copy it into A register content. So that is called register addressing mode. Next one, direct addressing mode. So address we have to mention, from the address we are going to take that, right? So that is we are going to load accumulator with 2050, right? So this is a direct address. So that is we are having now directly we are having an address, then this address data is going to be load. 2050, in the 2050 what's the value, then we are going to have now, right? Then we are having the in 35 also, we are having now direct addressing, right? So the address is port address. Here 35 is port address. Here 2050 is memory. This is memory address. This is the IO address. So memory and IO we can send the data. So that is we are having now direct addressing mode. Then register indirect addressing mode, right? So we are having now the KCL pair content, right? So KCL pair content is there. If you are using that M, then this M denotes KCL pair address, right? So this is a KCL pair. In that KCL pair, we are having some value 9050, where we are having now some data. The data is going to come to accumulator. Right, so like that we are having now LDAXP stored XP, so we are having now the directly we are using now, right? So register indirect addressing, so that one is in that address what we are having now the content is going to be loaded, right? Move the content of PC register to the access. Next one, implicit addressing mode, right? Implicit addressing mode means the address is not mentioned, then we are having now that automatically will get, right? Complement accumulator. So that is we are having now. Then we are having CMA direct instructions there. Then if you are giving the CMA, A is not allowed, right? So this is full instruction CMA. Next one, rotate right, rotate right that accumulator, right? So that is also we are having implicit data, RLC implicit data, right? Then the relative addressing. So what do you mean by the relative addressing is we are having now move R0, comma 05, right? So that is we are having now 05. We are having A equal to 55. Then we are having now that R0 is here we are R0 is moving to A. Then A register is separate and R0 is separate, right? Right, so we are having now the jump instruction here relative addressing. Here that again uses relative address, right? So that is relative addressing means here then this is going back to this location. So we are having now the link with some relative addressing mode. So that is called relative addressing. Right, once again then I repeated that one. This is important actually. So we'll see that. Then type of addressing modes, right? So that important question. So they have to mention about the type of addressing mode. So that immediate addressing mode is the data itself in the instruction is having the data. That is immediate addressing mode. Next one as we are having now register addressing mode. So we are mentioning that register, then register content is going to move now. Next one is direct addressing. So in that instruction itself we are placing the address. Instruction itself we are having the address, this direct addressing mode. So in that address we are having the data. So that is direct addressing. Index addressing mode, right? So here we are having now register. So move, then we are having KCL pair, then KCL pair address, then move to A, right? So here we are having now move the content of PC pair register to accumulator PC. Then store the accumulator content in memory pointed by the register PC. And do. Right, implicit addressing, that is CMA, there is no argument. CMA itself complement accumulator. Then RRC is rotate right accumulator. And RLC is rotate left accumulator. Now the relative addressing mode is here we are giving that again. So the again is the address, then where we are having the corresponding address. Okay, sure. So these are the possible indirect addressing mode. So they may ask questions: immediate addressing, direct addressing, indirect addressing, register addressing, and index addressing, relative addressing, memory mapped IO addressing we are having now. Right. The advantage of addressing, right? So we are having now the versatility. Then we are having we can have many methods. Then we are allowing that one method, and we can manipulate some operation, right? So we are having efficient memory use, right? So we are having the direct addressing mode allow that efficient use of that memory, reducing that memory footprint or program by making the best use of availability, right? Next one, easy to use, right? So that addressing mode is very easy to use, move, or easy to use, and improved performance, right? So this is going to improve the performance. Disadvantage, the code is very complexity, then overhead for changing the data. So we are having now the debugging is difficulty, right? So from here we are executing, then it will go for the another machine, then we are moving that one, right? So like we are having now that particular instruction is some difficulty in the movement of table, right? So next one is here we are having now limitation, right? So the limitation is here addressing mode are limited by the size of the program counter. So that one is here we are having only program counter is only 2 byte instruction. That 2 byte instruction we are using, that one we can move, right? So addressing mode is we can usage is much more, right? So here we are having now the direct addressing. The direct addressing use when the address of the operand is directly specified in the instruction. So that is move immediate a comma 00. This addressing mode is used for simple operation. Okay. Next one is indirect addressing. Right. So in that indirect addressing, the address of operand is not directly specified in the instruction, right? But instead the stored in the registers and memory, right? So we are having an indirect addressing. Immediate addressing, right? So we are having now the corresponding code itself. We are having that address. It's immediate addressing. Register addressing is, sir, we are going to have a PC pair, HL pair, like we are having now that register addressing. Okay. Right. So we are having now some challenges in the addressing mode. The limited addressing range. So in the addressing mode is having the limited addressing range, right? So that is we are having now that some area is not specified as a storage area. Then we are using now that it will give the wrong result. Next, the complex instruction set, right? So in that instruction we are having somewhat complex LXIH, and we are going to have now the top code, like we have to consider now, right? Then limited addressing mode. So we are having now that some other processor we are having many category of addressing mode is that. Here we are having now there's some limited addressing mode. Stack management, use of stack point register can be challenging, right? Especially when dealing with nested subroutine and interrupt, right? So that is we are having now stack management, right? So I told you that one we are calling the function, we are having now the stack, right? Then performance consideration. Some addressing mode, some addressing can be costly, then other may be somewhat different, right? So register and indirect. This means that the program need to be carefully consider which addressing mode to use optimal, right? So many type of addressing mode, then how we are placing the data, and if our intended data we have to take it out by in what way. So that is we are going to see in that one, right? So memory management, right? So memory management is here we are having now we are storing the data in one memory. If you are retrieving, then the particular memory is idle, then the memory is going to be used for other. So for that one, we have to do that through management. Memory management. Okay. Right. Today, actually, we studied about the subroutine and stack and subroutine, and we have seen that one addressing mode, right? So that one is we are going to see. If you are having any doubts, you can ask now, right? Then we can stop here, right? If you are having a doubts, then you can ask. Otherwise, you can leave now.